In this video, we're going to look at the reactions of alkali metals. So three key things that we need to think about here. So we've got the reactivity of alkali metals with water, what the reactions look like, how we carry out the experiment, and what you'll actually see. We need to explain the reactivity of the alkali metals in terms of the atomic structure, and then we need to be able to write equations for the reactions of alkali metals and water. So the first thing we need to think about here is what would happen if we put the first three alkali metals in water. So we're looking at the group 1 metals, lithium, sodium and potassium. What would you actually see if you were to put them into a big bowl of water? So I've drawn an example here. I've drawn some lithium, some sodium and some potassium here on the top of the water. Now the first thing to note is that the lithium, the sodium and the potassium are all less dense than water, so they'll actually float on top of the water. So you'll actually see a piece of the metal just floating, bobbing around on the top of the surface. The next thing that we're going to see is that we're going to see a bit of fizzing around the metal when it's placed in water. So we're going to see some fizzing of the water as we produce a gas from the reaction. So we're going to produce some hydrogen gas from all these reactions, which we'll look at in the equations in a moment. But we've got some bubbling here. You can see as you move from lithium to sodium to potassium that the bubbling gets more vigorous. The reaction gets a little bit more excited. So we got some fizzing here jumping out above the water for the sodium. And then we've got the reaction here of the potassium where you'll end up seeing a lilac flame as well. So we're seeing as we go down that group from lithium to sodium to potassium, reactivity is increasing. Going from that lithium to sodium to potassium. And that's a trend that you'll find throughout the group. So you could move on and you could look at rubidium, cesium. As you go down that group, they'll get more and more reactive as you move through. So the reactions will get more and more vigorous with the water, leading to an explosion if you were to drop in rubidium or cesium. Eventually, the metal will end up disappearing and the gas is given off, it's released, and you won't see anything left over. We're going to look at what would happen in the solution later on, because you can see a change in the water if you put some indicator in there as well. So that's one thing that we're going to look at in a moment. The next thing we need to look at is explaining the reactivity of the metals and why reactivity increases from lithium to sodium to potassium. To explain the change in reactivity, the increasing reactivity from lithium to sodium, what we need to do is look at the atomic structure of the different atoms, and we need to think about why these particular atoms are reactive in the first place. So you'll notice here I've drawn out the structures of lithium, sodium and potassium, and each of them I've drawn the outer shell electron here in green. Now you'll know from the formation of ionic bonds that atoms are unstable until they have a complete outer shell. So these three atoms are particularly unstable because they have one electron in their outer shell, and they'll need to lose this outer shell electron in order to form ions, like for example the lithium ion here, the sodium ion here, and then the potassium ion here. Just get a bit of room. So once the outer shell electron has been lost by the atom, we've then got complete full outer shells of electrons, so we've formed stable ions here with that full electron configuration. To explain the reactivity, we need to focus in on these structures. So we need to think about the number of shells these atoms have got and the number of electrons they've got. So we're saying that reactivity increases from lithium to sodium to potassium. Now that's increasing reactivity as we go down group 1. Now if you look, as you move across, you get more electrons. So sodium has more electrons than lithium and potassium has more electrons than sodium. So as you get more electrons, that ends up getting more shells, and that creates shielding of the nucleus. As a result, the atoms get larger, and as the atoms get larger, this outer shell electron is getting further and further away from the nucleus. So the outer electron gets further from the nucleus, And it's this positive nucleus which is actually holding the electron here in the first place. So it's the positively charged nucleus which is attracting this outer shell electron. So as the electron gets further from that nucleus, it gets further away from that positive attraction, and therefore this electron gets lost more easily. Now you should be able to therefore predict the trend down group 1 beyond potassium into rubidium, into cesium, into francium. So what you should be able to see is that because the atoms always get larger going down group 1, they get more and more reactive, their reactions with water will get more vigorous, and that's because their atomic radius is getting larger, the outer shell electron is further from that positive charged nucleus, so it's lost more easily. Now the final thing to look at for the reactions of alkali metals is the chemical equations for their reactions with water. So first of all, what I'm going to do is draw a general word equation and then a general symbol equation, and then from that we can build any of the symbol and word equations. So the first thing that we would have is we would have the metal that we're adding, so we've got the alkali metal, add it to water, and our first product is going to be a metal hydroxide. The gas that you see given off is hydrogen. And this is the gas that will end up exploding at the end of the reactions. Now with the metal hydroxide, we can see that a metal hydroxide is made because the water will have turned alkaline, and we can use an indicator to actually show this. So if we added a bit of universal indicator into it, we'd see a purpley blue colour for the solution as we produced a metal hydroxide, which is an alkaline. And this is why they're called alkali metals in the first place, because when you react them with water, they produce metal hydroxides. So they make an alkaline solution. Now, a general symbol equation for these reactions would be a solid piece of metal, the alkali metal again, added to water, gives us the metal hydroxide, which is aqueous, and then hydrogen gas is released as well from the reaction. Now, this is just general metal equations, so it could be any of the metals in group 1. Now, to construct the equations, all you have to do is replace the name metal here. You wouldn't put the alkali into the actual equation, just replace the name metal here with the particular metal you're using. So for the first example, lithium plus water is going to make lithium hydroxide, and then hydrogen gas is always produced. Another example, looking at the symbol equation, so if we use, say, potassium for this one, all we need to do is have 2 moles of potassium, which is our solid metal, reacting with 2 moles of water, which is our liquid. We have 2 moles of our potassium hydroxide is made, and that's aqueous, dissolved into solution. And then 1 mole of hydrogen gas is released from this reaction. So there we have the key things that you need to know about the group 1 metals. Thank you very much for watching. Please like these videos and subscribe, and keep on watching.